All right, welcome to day 2 of chapter 18, which is elementary chemical kinetics. Today we're going to see the solution to second order differential equations, that is second order rate laws. Then we'll take a look at a couple of other different elementary reaction steps, including sequential reactions and parallel reactions. First, I'd like to show you the solution to the rate laws for a couple of different types of second order reactions. And the first type is the situation where 2 moles of reactants form some products. In this case, the rate law, if this is the slow step of a reaction mechanism, then the rate law is going to be the rate constant concentration of A squared, like so. So I'm going to give you the solution to this differential equation straight off the bat. 1 over the concentration of A at some later time is equal to the 1 over the starting concentration of A plus 2 KT. So we already saw the solution for the first order rate law. This is the solution for a second order rate law, which is second order in one of the reactants. And the half-life in this particular case can be found using a similar technique as we did for first order. It becomes 1 over 2K starting concentration of A. Okay, the second scenario that we're going to see is the case where there are 2 reactants and both of them appear in the rate law expression. So A and B react together to form the products. By the way, it can often be convention to write the rate constant value directly above the arrow. So now in this case, our rate becomes the rate constant times concentration of A times concentration of B. So now when we solve for this case, we get a fairly complicated expression. Starting concentration of B minus starting concentration of A times the natural log concentration of B at some later time divided by the starting concentration of B, starting concentration of A at a different time divided by starting concentration of A, all equals KT. So as you can see, this is a complicated expression, but I just wanted to write it down to show you that there are solutions to these rate laws of higher orders. Though the higher the orders get in general, the more complicated these solutions become. And later on when we get to more complicated situations, we're going to have to rely on some approximations in order to even begin to approach the solutions to these kinetics problems. The next situation I'd like us to consider are sequential reactions. And so here's what a sequential reaction would look like. Substance A reacts with some rate constant K1 to form B, which then reacts with some rate constant K2 to become C. Okay, and that's sort of what's being depicted over here in this graph to the right. And so I'm going to write down the rate laws for each of these, and then I'm also going to give you the solutions. So the first rate law is that the rate of change of A is going to equal the negative rate constant times the concentration of A. So this is just like a first order decay. And we've already seen the solution to it. The solution is the concentration of A at some later time equals the starting concentration of A, e to the negative K1T, like so. So now when we want to think about the formation of B, it gets a little more complicated. The rate of B concentration change with respect to time is going to be partially thanks to how fast the first step of the reaction goes, depending on the concentration of A, but then also how quickly B disappears. So it's going to be the rate constant K2 times the concentration of B. So as you can see, B is coming from this part of the reaction and it's going to that part of the reaction. There is a solution to this one, and it is more complicated than the solution to the first step. Concentration of B equals K1 over K2 minus K1 times e to the negative K1T minus e to the negative K2T, all times the starting concentration of A. Okay, so this first expression here, I'll use in blue, this first expression here describes this curve right along here. And then this expression here describes this curve right here. Okay, because that's B. At first it's formed in high amounts and then it peaks and then it kind of slowly decays off. And that's what this function is describing right there. So now let's take a look at the final rate law. Rate of change of C with respect to T equals K2 concentration of B, because that's where it's going. C is, that's where it's coming from. C is not going anywhere, so we don't have any sort of addition or subtraction there. And the solution is that the rate of change, the concentration of C, equals a fairly complicated expression here, K1 e to the negative K2T minus K2 e to the negative K1T over K2 minus K1 times the starting concentration of A. And so that function there is what describes this curve right here, the concentration of C. So we know the functions for each of these for the sequential reactions, and in the next video we're going to see an approximation that's going to make all of these expressions a whole lot more simple.